Hi, this is Hanadi Mohammed. I'm presenting quantum machine learning, which algorithm, as part of the final project for quantum computing for computer scientists. So when we talk about quantum machine learning, we're still talking about supervised learning, unsupervised learning, reinforcement. But in this case, we're adding to this the quantum algorithm that actually make use of quantum computer features, such as superposition, entanglement, and interface to encode data. So we'll see how we're going to implement by using an example in this presentation. The algorithms that actually adopted in quantum machine learning, like there are some of them here. So we have Grover's algorithm, which is used in, we know that it is used in the database searching, k-medians, hierarchical clustering, neural networks, nearest neighbors. It's also worth mentioning that it is actually, it is observed that almost 50% of the quantum learning algorithm rely on Grover's search application or one of its variants. Also, we have this Harrow Hasidin Lloyd algorithm, which consists of solving a linear equation set that can be used in different machine learning models, like linear regression, support vector machines, recommender systems. There is also quantum phase estimation algorithm, which is using the quantum Fourier transform, and it is used to get the point details through eigenvalues. The phases in general for the quantum quantum machine learning is actually going through the data encoding, which is an important step. That's why we're going to talk about it in the coming slides. And then we have the processing through quantum circuit, which is including this kind of regression and all this kind of classification. All that is done through the quantum circuit. And then we have the normal steps of minimizing loss function and calculating the loss function. We'll see all that these phases through the coming example. So the data encoding is basically an essential part of quantum machine learning, and it has different methods. We have the basic encoding, amplitude encoding, angle encoding, and arbitrary encoding. Here, we have, I focus on these two just to have this kind of intuitive, what is actually data encoding. So here we have the basic encoding, which is actually the entire data is represented as superpositions of the computational basis state. So we have here our example. We have this data set, assuming that X is a data set here, and then we have, it's including only these two. So we have X, the first element is 101, and a second element is 111. And you know, these are binary numbers, basically. So we have, so for that, we need three qubits, basically. And we know this is actually 5, and this is 7. So if we look at the how to represent that, basically before we're looking at this, how this is encoded is basically the we use because we need these two elements. So we have this is going to be represented as 1 over square root of 2 multiplied by this is 5, and this is the first element here, the x1 and the x2. So that is going to be implemented in programming part. So that we specify the desired state as this. So we have, this is, if we look at that, this is 0, 1, 2, 3, 4, 5, and this is 6 and 7. So we can see here 5 is actually multiplied by, or actually replaced by 1 over square root of 2, and the same thing for the 7. That is actually going to be passed to the quantum circuit, which is actually defined by 3 qubits, and then using the initialize function to have this a desired state to be passed to it, and then we will be able to demonstrate it using this decompose method. So if we look at that here, let's look at it in the program. So I have here. So this is the basic encoding. So you can see here, in this example, I made it, these are 3 actually. So that's why we make it with square root of 3. So this is 0 here, and this is 2, right? 0, 1, 2, and this is 7. So in this case, we have, it's the same thing, but it's basically, we have only 3 elements. That's why I made it with 3. Because if we have like, still we keep it with square root of 2, we're gonna have an error. So it depends on how many, the values, the number of values. We learn that in course. So we have here, this is basically, we're gonna see, when you run that, we can see basically, this is actually the circuit. And you can see the difference here, basically, it depends on the value that we use. So we can see here, let me make it bigger. So here we can see the rotation, or the value of the rotation is changing here. This is basically 3 pi over 4 here. And if we look at in the presentation, because we're having different values, the difference is here. So the circuit is the same, but the value of rotation is the one that is changing. So that's for the what's it called? For the basic encoding. For the other encoding, as I mentioned, I'm going to talk about 2 of them. For the other one is the amplitude encoding. So if you have these, the amplitude encoding is basically, we have n qubits that represent a normalized classical n-dimensional data set. So if we have here, these are 2, also 2 points, and we're going to normalize the amplitudes here. So we have, this is going to be square of 1.5 square plus 0 square force, and then 4 plus 9. So that will make 15.25. So we're going to normalize using this 1 over square root of the amplitudes, and then we're going to do it that way. So we have, this is going to be the value. This is, we're using 2 qubits. So basically we have our values in this case. We have 0 here, and this is 2 and 3. So that would be used here, and then we're going to in the same way. After that, we define our desired state that way. So we have here, this is for 0. Yeah, this is because this is 0 point multiplied by 1.5, and the same thing here, 1 over square root of 15.25, and the same for the 2 and 3. So this is 1 here is will not actually. And we have, again, we can see here we have the rotation value here. So now we will look at the Qiskit platform, since we're going to use the Qiskit for implementing our machine learning example. So the building block for the Qiskit here, we have a collection of computational units, okay, that include different groups of quantum neural network and quantum kernels. That's basically what we have here. And also these computational units will be used by the redresser and the classifier to implement the algorithm. And that will be after that connected to the PyTorch using the torch connector. So this is basically our platform for the Qiskit for machine learning in Qiskit. So what we're going to do in our example, we are using the modified National Institute of Standard and Technology, which is known as MNIST dataset. So we're going to use this dataset, which is actually, the dataset is huge. It has 60,000 hundreds of single-digit image. Each image is the size of 28 by 28 grayscale pixels. So yeah, there are different platforms, but in our case, we're using the Qiskit, but other platforms is basically, there is one from Google, which is TensorFlow Quantum, and there is Penny Lane, open source software, and there is Pakewill from Rigetti Computing. So these are different platforms, but we are going to use the Qiskit platform. So let's go to the program and see our example. So this is just for clarification. I found this in Qiskit tutorial. They have this, and it was basically like this is another example. So there are two examples that is mentioned on that. So here, basically I have, of course, this is the important that we need in our case. And here for implementation, we need the torch package to be used for some mathematical functions, optimization, and loading data. So after this is basically the one that we already have it automatically, and this is a second one. So let me just make sure I'm running it. And here, after doing the imports, the additional imports basically, and then we're going to load the data. We know that when we load the data, we need two parts. We need testing part and we need the training part. So and usually the testing, the training is bigger than the testing, and it's always supposed to be different. Other than that, it's going to be just, it shouldn't be the same data. So we have here the program. So we have this basically the first parameter here for the loading the data. We need, this is basically where we're going to import the data from. And the important thing here to have the data for training, we have to make training equals true. And then the other thing is also we can see that we have the transform function. So we have the transforms, which is basically going to having this data, which is coming, which is basically it's called PIL, which is Python image library, and return the image in a tensor form, which is going to be in the range of 0 and 1, between 0 and 1. So it is going to transform the version from between 0 to 255 into basically normalizing it. So this is step in the classical one. I remember there is a step to normalize these values. So here it is going to be directly represented that way. So we have the data basically after defining all that. So we have our data, we specify we need this for training. We also need to filter the data. The focus will be only on 0 and 1 values. So this is a step that is going to filter our images. And then of course we have basically now our data is ready to be used. Then after that, we have this part of the program is just visualize our data. So we have here like 6 samples only is used. And by the way, here I forgot to mention that there are 100 samples here to be when I see like this is actually to have 100 samples from each, like 100 zeros and 100 ones. And here this is just to visualize only like 6 samples. So if we run that, I forgot to run this part. So this one, if we run it here, we're going to see zeros and ones only. And then here, this is for the testing. So we prepare also the data for testing. So we're going to have like only 50% of what we have. Like if we here we have 100, now we have only 50 samples. So and of course this is not the same one. So basically when to make it for testing, we set the train to false here. And so that's basically what we have here. And here again, we're gonna make sure that we have only zeros and ones. So that is actually going to be our testing data. The next step is basically defining the quantum neural network and the hybrid model. So for that one, we're going to have a combination of classical neural network and parameterized circuit, which is actually containing the input parameters in the feature map and the trainable weights in the answer. So basically that's what we have here. We have this is for the parameter and this is for the trainable weights. And then here we define the number of qubits in the circuit. And then to combine them, we use this compose function. We'll combine these two to make it in one circuit. And then basically this is going to have like, yeah, this is basically what we have here for like one circuit. And then after that, we're going to have the estimator function. The estimator function is taking these, what's it called? Taking the parameterized circuit input and weight as input. So this is basically here we can see we have circuit, we have the maps, the parameter, this is the input map feature. So we have the feature and the weights. And also we need to enable the input gradients to have the hybrid gradient. So we need to set that as true. This is an important step. So after that, yeah, I wanted to show also here. Let me say, if I say print here, I will be able to see the combined circuit. You see. If I run that, I'll be able to see, yeah, this is, as you can see here, we have, this is combined together. So after that, we are going to have, since this program is actually for recognizing this program for recognizing the images, we have to have the convolution process to help extract some features. So the net class is needed to define the fully connected layers in the neural network in the init function, which is here. And then to build the first 2-dimension convolution layer, we use this prompt 2D, which is basically accept the input one channel, which is the input, the image, basically, and then output the convolution feature. Here we have going to be a 2 convolution feature, and then we have the kernel size, which is 5, which is 5 by 5. And then for the second dimension convolution layer, accept this is the second one, accept this 2 input layer and output it into 6 convolution feature, and the kernel size is 5 by 5. So the drop function, the drop2 out, drop2d function is used to ensure that the adjacent pixels are either 0 or active. And then we have the linear, we have 2 of them. So the first one with the 256 and 64, this is used to create the first fully connected layer. Okay, and then the second one is used to create the second fully connected layer. Then the torch connector here is applied. So torch connector is used to connect the Qiskit quantum layer, quantum neural network to PyTorch. So this is where we have the PyTorch work here to connect it. The torch connector to connect with the PyTorch. And execute the image classification. And then after that, followed by linear to generate a one-dimension output. The second function, forward, is used here to specify how data will be passed. So that is actually is used to create, how the data pass, so that how they will be passed. First, pass the data through the conv1. So this is the one that we have here. And that will be passed through, which is used to as a parameter to the rectified linear activation function, which is called relu here. And this is, after that, we use the second run max pooling over the return value from the relu and repeat the function. So that's basically you're going to see here, it's going to be repeated after that. So that is actually this part for defining the neural network module. Then we have the training and loss function, basically. So this model is basically used the method for stochastic optimization, which is Adam optimizer, with learning rate 0.001. So the learning rate is actually controls how quickly the model is adapted to the problem, and which is actually ranging between 0 and 1. Then we have the negative log likelihood loss function. So this is implemented to train the program and calculate the loss function. Okay. We have here, did I run that part? I forgot to run the previous one. So here, this is basically for training the model. So we have, after defining that, we will have the number of epochs, which is here in this case is 10. And this part is very slow, by the way. It takes very long time to be running, surprisingly, actually. So I'm surprised with this slowness, actually. So when we run that part, we see like, so that training 10% and then 20 up to 100%. And every time you see like it is actually a very small number, since it is negative number, which is a good indication and shows how accurate it is. So as a proof, I will click on that, but it's going to be like taking a long time. But while that, I'm going to continue we're talking about the rest of this program. So the other part here is basically plotting. So I'm going to plot the result from here, and that is going to be shown like how this program is like converging to the nearest result, which is actually very accurate. When we have for testing this model, or for saving this model, basically we're going to save this model here, and then for evaluation, I hope I can run that. I don't think I can run this because it's still running here. But basically for after having this model here saved, you can use it for evaluation. And this is basically like a call for what we have in the previous. So that is going to be assigned to quantum neural network 5. That's create a neural network, which is a method that we built here in the previously. So we have, we call this method, and this one. The next one is for the net, the second one. So you pass the quantum neural network to the net function, and then you use the model that we saved for running it. And basically, it will tell us the result is all key matched successfully, which is very accurate, actually. And and after that, we have set the model to evaluation mode. So now we have basically this is for for the evaluation. So this is this is basically for testing the last thing for to evaluate the program. And then you can see here we have this is yeah, there is, yeah, this is what I was thinking of. So the no grad functions, which is a mode of the layer to evaluation mode. So here, that's to evaluate the program. And basically, we have, this is, here in this case now, it says 99%. But I have it, when I run it, it was 100%, which is really, really, like, I was impressed with 100%. So basically, and then after that, this is for plotting. I hope that this is like start here now. Still working. See, now it is started at 10%. So I'm going to continue to talk about the last part. So the last part is showing actually the predicted data. So you can see here that predicted data is actually, here you can see like this is predicted, this is one, and as you can see, this is actually really accurate part. So that is, I'm just putting that to show how slow it is. So this is still working. So I'm gonna leave that and go and talk about the results and discussion. So as we saw, basically now it is saying 90 something. I will go back probably. I will check it out again because when I ran it, it was 100%. And I think it is in the report. I made a screenshot for that. But it is very accurate in general. But the program is recognizing only zeros and ones. And we saw also how slow this program is. So yeah, that's actually probably this is going to be fixed in the future because I'm still working on some updates. Even while I'm working on this project, there are some update. The course that I was using for learning quantum machine learning is moved completely, and they put it in GitHub. That's another example of what is going on here. Still, there are what is going like they're still doing some updates and are doing some further things that is still showing that they're not completely ready for that, and that's my opinion. So hopefully in the future this is going to be fixed, and yeah, that's another thing. So that's the slowness is, as we saw now, is very slow. The potential application, well, what I'm thinking in this is for me is a starting point. So I'm going to go for further studies on the quantum machine learning. That's my interest, and that is where I'm going to dig deep for my thesis. Writing papers is other goals that I'm planning for. Participating in conferences, that is something that is really I'm interested in. And of course, I'm going to look at the other platforms. I'm not going to stick on Qiskit. One of them, probably I'm going to look also at the Google platform to see how these are implemented. And as I mentioned, Grover algorithm is 50% of the what's it called, quantum machine learning are using this Grover algorithm. I'm gonna dig deep on that and see the potential of implementation on this using this algorithm. So now let's go back and see here yes, it's still working on that. The other thing that I wanted to mention is when I said we have it's only working on zeros and ones, I tried to change this program, which is basically the same program, and I tried to change it to having it with 0 and 2. I tried to even change it to 2 and 3. I had an issue with that, so I'm not going to run all that again, but it's basically, I'll show here, here, for example, it's going to show the error anyway. So I'm going to show this part here. This is working, and this is basically the same thing for downloading and defining our training data. And here, this is, I made it download to see the indexes, but here is, and to see the size as well. But here, basically, I tried to, I run that will work fine. And you will see basically that it's basically we have here 0 and 2 showing. And for the test, this is the test part. It is working fine. The other, again, I showed the index, and this is actually also I was able to see the data. This one I can run it again because I was trying to do the 3. So here, this will show me the data. So now the problem is, oh yeah, here I didn't change that. That's supposed to be 0 and 2, the same like on top. So that is here, and this is the 1. So now if I run that, it should show me 0 and 2. Now here, this is the size, and here this is the same thing that I did. So yeah, that's for defining the quantum neural network. And here is the neural network module. And yeah, that's fine. Now when we come here, the problem was here. So this is what we have. So changing only from 0 to 2 will bring this problem. So that is another thing that what I found or faced in this program. So it's only, until now, this program works only to recognize 0 and 1. So here, this is another, and again, still working and showing how slow is that. Now we are only in 40%, but that's basically the idea of showing how slow the program is. And I think that's all for this presentation. And thank you so much.